CLion, a cross-platform IDE for C and C++. Download now.
Hello, everybody. Let us begin. This time we are going to talk about parsing C++. It's a big topic, I know, but we'll try to keep it kind of not really long. My name is Yuri. I work at PVS-Studio, and it's a static analyzer, and I'm working on the core component of C++. And like said, we'll talk about parsing. But first, let's just take a quick look on what parsing is about. Let's say we have something like that. That's our input in characters. Basically, it's just a huge string. Well, not huge, but string. And it goes to the part of a parser, which is called lexer, which knows, according to some rules, how to classify those characters it gets. It goes one character at a time and produces something like that. Groups of characters with labels on them, which are tokens. And then the parser itself takes over, and its job actually is to tell us, is it okay or not? Is our input okay in terms of the language we are working with, or is it not? But that's not useful. Like, we don't want to get just a Boolean answer, true, false kind of thing. So what we do usually instead, we still get those answers, but the positive answer that, the input belongs to the language goes in terms of, and something like that, it's a syntax tree or AST. Well, it looks more like that really, but hopefully you get the point. We take the input and we build kind of a tree-like structure from what we get in order to traverse it later and do something with it, like code generation, evaluation, or something. And how does the parser know like how to deal with input? It knows it based on grammars. Well, everybody is familiar with the notion of grammars. Like in English, we have this standard subject-verb-object structure of a sentence. And if we look at it from the grammatic standpoint, here are our subject, verb, and object, the main parts, and we can build something of a syntax tree as well from just basic English. And if we pretend this is a programming language, well, essentially we get a binary expression here. So we have two operands and an operator, which is the verb. Now, grammars, there are different kinds of them. They kind of start from the basics, and the more advanced grammars incorporate more basic ones. Like, for example, regular grammars, they deal with regular expressions. Context-free is what most of our programming languages use, and context-sensitive grammars are really the most complex of them all. They include like tag language, where you have sentences with the equal number of letters. And as it goes, usually more advanced grammars are easier for humans to understand and use, and more basic grammars are easier for machines. So if you try to speak regex, you probably know what I mean. And if you ever try to teach your machine understand English, you also probably know what I mean. Well, without neural networks or anything. And there are different ways of like writing them down, but we'll make a small nonsensical language just for the sake of demoing it. And I'll use the notation which is used in the C++ standard, a human readable. Let's see how it goes. Our small language will have expression lists, which consist of expressions. And expressions in a list will be separated by commas. And this here is an expression list production. And this is a non-terminal production. There are two kinds, terminals and non-terminals. Non-terminals are defined in terms of other productions, and terminals are not. We'll see in a second. Okay, so for expressions, we'll just have binaries. And for binaries, well, we will take IDs and join them together with an operator. And quite frankly, since we don't care about semantics here at all, we'll just say that we have A, B, C, and D as our IDs, and $sign as our operator, the binary operator. We don't know and we don't care whether or not they mean or do anything. We just care about syntax. Frankly, they don't really mean anything. And let's see what we can write in such a language. Well, we can just use A. We can use A, B, C, for example, as like an expression list of IDs. We can combine those IDs in binary expressions, separate them with commas, and so on. So let's see how parsing goes of that. Now, there are different kinds of parsers, and they all kind of broadly classify as either descending or ascending methods. Like the good old recursive descent we all know and love is a descending method, and let's say something a Python, which is a parser generator, can make for you. It makes an ascending parser. But let's try and parse this expression here. A something, B something, C. So descending first, recursive descent. It is kind of important to note that descending and ascending, these words relate to the way we traverse the grammars and not the input. So in descending parsers, we go from the top grammar production, which is our expression list. So we go expression list, then we go into expression, then we go into binary, D, and here we bump into A. And since we can't go any further, we are at the very bottom, at the most elementary production. This is our ID expression, A. And as you see there, A became kind of grayed out. That's because we are past it now. And we are still in the binary expression production. And we are looking for the operator, for the $sign. Here it is. And then in the same way we did with A, we descend down to ID, we consume B, and here's our binary expression. This is a part of the AST. And it continues. It continues until it reaches the end of input, and in expressions until it consumes everything it can, kind of related to the expression. So in our case, both happen simultaneously, so we get to C, and we finally are able to build an AST from it. And if you look at it, we have two operators, the same operator, in kind of a big binary expression, a chain of them, if you will. And the tree grows to the left. And that is because our binary expressions are left associative. So when you have multiples of the same operator, they grow to the left. And if you have different operators, the operator precedence is encoded in the grammar itself. Basically, you are just calling functions. A descending parser will consist of a lot of functions which are named probably after expressions, after productions, sorry. Let's see how it could be done. Let's say we have a function somewhere in our parser. So we go parse left-hand side of our binary, we return it in the end, and between we have something like that. That much thing in while, it just checks if we have the correct token next. And the loop is needed in order to create this left associative structure I've shown you. And if you look closely, you might ask, wait a minute, the grammar, it says ID expression or binary $ID, but we are only calling ID expression in this function. Where in the world is this? Like, how is it handled? Well, the answer is it is handled inside the loop. And one of the reasons we do this loop, because recursive descent has limitations. And one of the big limitations concerning the grammar is that you cannot have left recursion. And in our case, with the binary, we have left recursion because binary expression depends on the binary expression again. And obviously, if we call binary expression from binary expression, we will just recurse and crash. Well, ascending parser could resolve this. Ascending parsers have less limitations than the descending parsers do. Let's see how it would work. I will not use the entire grammar here because even for our small language, it is too big. Let's take a look at these fragments, just a binary and ID. And for an ascending parser, you cannot write it manually, usually. It's a state machine with the transition table derived from the grammar itself. And that's why you need generators like Python or Yak or whatever. And you also have the state. You have a state which it's like a cache. It is a working memory of your state machine. And there are two operations, shift and reduce. Let's see what they do. So we are at the beginning of the input and we see A, and we shift A into the state. We do shift because the state is empty and we cannot reduce anything. The second operation is reduce. And now we've got our input, which starts with a $sign now, and we have in the internal state, we have A. So what is A? We need to decide. And here's why it's called ascending parsing, because we go to our grammar productions and we see that A is ID expression. So we perform the reduce operation, and our token A becomes an ID expression. And then on the next step, we still we are looking for productions which we can use to reduce our state. So since binary expression starts with ID, we kind of say that our ID expression is really, it belongs to the binary expression production. We do not create an AST node here for binary, of course. If we had one for ID, it's still there. Okay, now we cannot kind of reduce anymore. So we look at the input, we shift the dollar, we cannot reduce, we shift B becomes ID expression, and this part, this kind of state reduces to another binary. And then the process continues. Again, we cannot reduce dollar binary to anything, so we go to the input, we shift, and finally we get a resulting binary expression. Okay, so now you probably like that. So let's get on with it. C++. C++ is, well, frankly, it's my favorite language, but its grammar is extensive. What you see here is just, what do you call it? Just a table of contents for different grammar categories, which contain a lot of rules. But anyway, surprisingly, everybody, when parsing C++, seems to be doing recursive descent. Like Clang does it, GC, as far as I know, does it. I don't know what Microsoft do, because their compiler is not open source, but I bet they also have it. Why is that? Oh, because recursive descent, with all its limitations, is really convenient. You can write it by hand. You can tweak it to your needs. You can also kind of cut some corners and massage the grammar into a convenient thing for parsing. As you see here, with ID expression, which we call instead of binary, we just unwrapped the binary expression here. We are calling just ID. And that's possible because we can do, like, when we are writing something manually, we can do whatever we want. We don't have to like strictly adhere to the grammar rules. It's nice if we do, but we don't have to. And this was the example from before. And if we look at C++, well, nothing really differs in terms of expression. Again, we have different like operator precedence types, and they, inside of them, they depend on each other. So additive expression is plus or minus. Its operands, left and right, are multiplicative expressions, which is multiply, divide. And this is, by the way, how the operator precedence is encoded into the grammar. So this, quite frankly, is not what would happen in a real parser, because it's too, well, it leads to a lot of recursion. If you do it this way, like you're just making a function for every additive, multiplicative, logical or logical and so on productions. Usually there's the operation precedence parser where we have a loop and a loop inside a loop, and operation precedence can be parsed without recursion, basically. But anyway, that is a good enough thing to do. And it all would have been great if it wasn't C++, because C++ has really nasty kinds of expressions sometimes, if we are talking about expressions. This here is a lambda called in place. But what's interesting about lambda, it's function. So, well, it's not function, but it behaves like one. So we can have anything we can have in a function inside the lambda. We can have structures with their own members. We can have like declarations. We can have a lot of stuff. And what I'm trying to say here is, in order to parse just expressions in C++, you have to parse the entirety of C++ if you want to support everything. Well, because like here's the proof that lambda is an expression which is kind of weird expression because it has a lot of stuff like compound statements, declarators, and so on and so forth. And statements, which can be in lambda, can also be declaration statements. So it's time we look at declarations. And I'll, like a spoiler alert, declarations are the most wonderful thing we have in C++. Let's say we have those two before us, and we want to parse. Let's try to parse the second one with recursive descent, as we are using recursive descent because blah, blah, blah. I said it was more convenient and easier to implement. This red dot at the beginning, it will denote where our lexer is standing, like which token we're looking at, and below it we'll see the call chain, if you will, of productions. So go name declaration, name declaration, block declaration. We go block declaration to simple declaration. We still haven't moved. And by the way, if you see words simple or basic or something, like, be sure it will be the most complicated thing ever. But anyway, so here we have decl specifier sequence. We do a lot of calls, and we finally consume int, which is our declarator specifier sequence. A simple type specifier, by the way, simple. Okay, now we have a decl specifier, we have a declarator list. We go in, and here we have declarator through init declarator. And if we go into declarator, we have a noteptr declarator, which is like a declarator, a name without asterisks and ampersands and whatever, not a reference or a pointer. And finally, at some point, we get to the name of that declaration, of that declarator. Boom, we have int meow. And now this, I think, should make you worry a little bit because it's called parameters and qualifiers. Let's see how it goes. So parameters and qualifiers are in parentheses. So we have a parenthesis, great. And we get a syntax error. Like, why? Because we have two in parentheses, and that's not a declaration of anything. That's a literal expression in all kinds of sense, like it's a literal. Oh, okay. So what on earth is going on here, and how do we deal with that? Well, what on earth is going on is easy to explain. If you look at those two declarations, the first one is described something like that, and the other one is described something like that. And as you can see, there are two different things, but kind of similar things. They both start with the same thing. Remember the limitation of recursive descent about left recursion? Well, there's a second one, which is not that easy to avoid. You cannot have overlapping prefixes between two productions in your grammar for recursive descent to work. But it works for C++. We know it because compilers do it. So how? Well, first, the problem we are looking at, it even has its own name, and it's called most vexing parse. I think it deserves that name. Let's see how it manifests itself. So let's say we have a structure and another structure which has a variadic constructor. It accepts anything. And in our function here, what are these two declarations here? Well, they both are function declarations. The first one returns cat and accepts pause, and the second one returns cat and accepts pause, a function which returns pause and has no parameters. That is because the function kind of parameters and qualifiers production, it has priority. As why I started parsing from the variable when I was showing you how it goes, because the functions have priority, and empty parentheses just mean parameters and qualifiers empty, not like a function with 0 parameters. And the next one, this is a variable. This is where we create kind of a temporary object and pass it into a constructor. Why? Well, because the parentheses of the initializer, they have another pair of parentheses in there. It's a parent expression. It's an expression, so we are not looking at a function declaration, but rather a variable with an initializer declaration. I think it was a brilliant idea to make parentheses a valid initializer. It was great. Thank you, whoever came up with it. And all those cases are kind of simple, but they can get infinitely more complicated. Like the first one is a function which takes 4 functions as parameters, and the second one is a variable. And the only difference is the last bit of that thing in parentheses. Now, the problem with the most vexing parse, why is it so dreadful, is because here's what the ambiguity happens. And to disambiguate, here is where you should be. So you can't really know if you're looking at a function or a variable before you reach the end of the closing parenthesis. Here are our two kind of limitations of the recursive descent. The first one is solved with unwrapping the grammar a little bit. And the second one, the only way really to solve it is go to a certain point, go back and try a different route if you failed at the previous attempt. You could also look kind of further a little bit. Like, let's say in this our example here, we could have checked like, oh, there's two, so it's not a declaration for sure. Let's pick another kind of route. But in simple cases, that will work. In more complex cases, you just cannot look forward reliably. You will have to either go forward too much and be slow, or you could you will still select a wrong prediction. Okay, so here instead of making a syntax error, we backtrack and we go a different path. We try to get into that initializer bit to parse it. Brace original initializer we skip because it's not a brace or equal initializer. It should start with the equal sign or a curly, open curly. So we are confident we can go to parenthesis, expression list parenthesis, and 2 is indeed an expression, which is an expression list. And we have parsed this declaration successfully. Great. Are we done here? So is it fine? Oh, no, because backtracks, they can resolve the most vexing parse situation, but they kind of can lead to really nasty problems like an exponential complexity of your parsing attempt. Let's look at that, like how the exponential complexity arises. Let's say we have like this template, and the way we use it, we kind of instantiate it with the same template, instantiate it with another template, and so on and so forth, and it goes on. So if we take a look at it as a hierarchy, we'll see something like that. I think it's a pattern used sometimes, but it doesn't concern us right now. Let's see what happens here. So I'll just shorten those names. And here's the grammar at the right side, which deals with this type of declaration. There's type def there, so we know we are in some context which deals with types, and also there's class elaborated type, which hints that we are looking for a class or structure. So we start here, and at the right, simple type specifier, simple, which is bad, and it starts with something called nested name specifier. The apostrophe, by the way, at the end of the production name means that the production is optional. It can or cannot be there. So it's okay if it's not there. We go left to right, top to bottom. We go into nested name specifier. We go into the parameters of the arguments of the template, which are used to instantiate it. Eventually, we get into the simple template ID here. And it goes on and on. And finally, at some point, we get to the very bottom. So at each step, we go simple name type specifier, nested name, simple template ID, or template name, or arguments, or another type name, simple type specifier, and so on and so on and so on, until we reach the very last one, the innermost one. And here we are having a bit of an issue. This simple template ID is okay. It can be parsed, fine. But we are in the nested name specifier production. And the nested name specifier requires that the name we have just parsed end with scope resolution. If there's no scope resolution at the end, it is not a nested name specifier, and we do not have a scope resolution at the end. So what do we do? Well, that's the most vexing parse situation, really, kind of. So we go back and we parse eventually the simple type specifier, and we are able to parse just an argument of one of our nested templates. We parse the argument, we go up, and guess what we get when we go up the level? Up the level, we again, using the same logic, parse a simple template ID. We see that there are no : 2 colons at the end. And we backtrack, and we again go inside, and we backtrack, and well, it gets really messy. So what really happens here is we keep at every step, at every nesting of that huge declaration, we just keep going like that. Simple template ID, nested name specifier, no colons, go back, go try and parse simple template specifier. Here's our argument of the simple template specifier. Go try and parse the argument. Oh, it should be a nested name specifier. No : go back. And it goes on and on and on. And the more kind of nesting levels you have, like here, I guess, you know what? I guess my cat kind of broke my slides a little bit. Yeah. So at every step of this huge structure here, we try to go forward. Eventually, we backtrack. We go a step back. We go a step forward again. We backtrack at every step we go in, kind of, and this is where it becomes really, really looping around itself. It keeps looping and looping and looping. Like, no, that's the correct slide. Sorry about that. I was kind of confused. So let's say we have parsed the inner one successfully. Simple template ID, good. We parse the one it is passed into as an argument. We try nested name specifier. We parse simple template ID. We do not see : We backtrack. We try to parse it as a simple type specifier again, but this time we skip the nested name specifier, which is not there. We get into the nested one. We backtrack again while we are there. like here, and then it goes on and on and on. And more nesting you have, the more time you will spend there. So our experiments show that about 10 levels of nesting will be kind of fine, but more than that, you won't be able to parse the entire declaration. Okay, so how do we deal with that situation? Oops, sorry. Let's break our grammar here a little bit. The way we break our grammar is we introduce an expression which will emulate like most vexing parse in C++, back to our made-up language. Let's call it Joker. And the Joker, being a Joker, will start with a binary $, and a capital X at the end. It will end with a capital X. So it can only, the X can only be at the end. These are our valid expressions in our silly little language. We can also have now with the Joker something like that and something like that. And here highlighted are the places where our version of the most vexing parse will occur. And let's try and parse this one, this expression, the last one. And well, in order to avoid backtracks to lead with like backtracks within nested backtracks and backtracks inside backtracks, calling backtracks, what we want to do is parse this, well, preferably in linear time and not in some exponential weird time. So while we are going and parsing this, let's track our lexer position. We will track it in the tokens, and it's fine if you have like a cache of tokens. If you are getting tokens on the fly, like you ask the lexer, give me the next token, and the lexer goes and processes the input, you can use it like the position can be the an iterate to the input of something. But for simplicity, we'll use just the number of token, zero counted. So at the beginning, we are at token number 0. And this is A. So the normal recursive descent going inside until we hit the terminal. Now we remember that our current token position, token position is 1. We get to B eventually. And we build this part of the larger expression, which is our binary. Our lexer position will be 3. 3 is like the next after B. And now we are still in the binary expression production, and we see a $sign, and the thing we expect to see after the $sign is an ID. But as we will see shortly, it won't be the case. But in order to deal with overlapping prefixes, what we'll have to do is to remember which productions we've been able to parse successfully as we went. So in this case, like we have a memory-like stack, and we keep its state the idea is kind of stolen from the ascending parsers. When we successfully parse something, some piece, we will put it into that state. And when we use that successful piece in some other productions, we will remove it from the state. Like our IDs A and B would have been on the state, and then when we constructed the binary here, we would remove them on the state, and now we have successfully built a binary $A$B, and it will go on the state along with the lexer position which follows it. Okay. So now we are still in the binary. We consume the operator. Our lexer position is now 4. And here we hit X, which our binary expression does not expect to see, because it expects A, B, C, D, an ID expression. That's a syntax error. And we have to backtrack. We cannot build a binary expression like successfully. And you might ask, like, wait a minute, couldn't we have just, checked for X and returned joker instead of binary from the binary production? Well, we could. Like, we could do it without a backtrack, just by jamming an if somewhere, which will check if it's an X. Yes, and in simple cases, that would work, but in real world situation, it won't work ever reliably, because you are not dealing with like simple cases like checking for one letter or whatever. Okay, so we backtrack, and we backtrack into the beginning. Like, remember, our expression is now either a binary or a joker, and the binary failed. So we kind of roll back to the expression production where we started, and we know that the binary failed, and we go to joker. And the joker, it starts with the binary. Here's our binary. And guess what happens to be on the state, like at the first place there, binary. So we know that we want a binary. Our state has a binary. Okay, we take the binary. We won't even bother parsing it. We will just remove it from the state and say, oh, yeah, that's our operand. And now we can kind of successfully construct the joker expression. Now, how it applies to the previous example, which was kind of messed up, but let's see how it applies. We still go down as we did before. So we get here, we get to the nested name again. We do not see the colon at the end, but we know that we have just successfully parsed a simple template ID. So it goes on our state. Now at this position, we know that there was a simple template ID. We still backtrack. We go up into the enclosing template. And then we go inside to parse that. And since we have the simple template ID on the stack, we simply consume it from the state and say, hey, look, there was a simple template ID. So now our enclosing thing also becomes a simple template ID, which depends on another simple template ID. And it goes on up and up and up. And this is how it happens in linear time instead of exponential time. Like, it goes here and here. Just sorry, it was messy when I tried to explain this because my slides were for some reason messed up. Before doing that, we had to go all the way down, backtrack, go up, go inside, go like all the way down, backtrack, up, inside, backtrack. So every time we descended into any of those what do you call it? Template arguments, we had to backtrack repeatedly on our way up from the bottom when we came to the last one, and then we had to backtrack on every step back multiple times. That's what led to the exponent. And here the parsing is linear because we remember the last successful bit, and when we descend and we see there was a successful bit, we simply take it. We do not try to look inside it. We just take it from the state and and we go in linear time as it was supposed to go, as opposed to exponential time. It was a lot to say. And at this point, well, I'm done with the main presentation. Questions kind of were expected to be here. But I guess I'll meet you in the room for our track, and if you have questions, I will be happy to answer. So thank you all for listening.